Hello, my name is Matthew Goodliffe and I'm the head of cybernetics at RACE, the Centre for Remote Applications in Challenging Environments at UKAEA, the UK Atomic Energy Authority. For over 40 years, Culham has been home to the world's largest fusion experiment, the Joint European Torus, JET. Since it began operation in 1983, JET has made major advances in the science and engineering of fusion, but in order to do so, has had to be serviced, maintained, and significantly upgraded in order to continue to push the boundaries of fusion research. For the past 20 years, this responsibility has primarily fallen to the Remote Handling Department, which in 2015 became RACE. The remote maintenance of JET is a highly complex and ever-evolving operation. The tasks required in order to upgrade the machine are the result of advancing science, and therefore are always changing. The technologies available to us to complete these tasks are also advancing, while previously used technologies are becoming obsolete and unmaintainable. Because of this, the JET remote handling solution has had to adapt, extend, and in some cases be completely redesigned in order to keep up. But these problems are not unique to fusion maintenance. They are true of all long-term robotic solutions, such as those required for fission and nuclear decommissioning. Solutions must consider the requirements not just of the present, but of the future, over decades of operation. Building on the experience gained from 20 years of remote operations, we can establish a number of major challenges that must be considered when developing a solution for long-term robotic maintenance. Where possible, we at RACE try to use off-the-shelf solutions to problems. The use of industrial robots, established tools, and pre-existing software packages can save time and money and reduce certain risks within a project. However, this approach often comes at a price, the price of integration. Integrating products from different suppliers often means dealing with multiple interfaces, many of which are bespoke to the particular manufacturer, and getting them all to talk to each other can be challenging and time-consuming. As previously mentioned, another challenge, particularly to long-term maintenance, is the ability to adapt to changing requirements. Over time, the tasks required of a robotic solution are almost certainly going to change. This can be due to a number of factors. For example, changes in the environment, its condition or its purpose, changes in technology, the introduction of new technologies, increasing capability and making certain processes more efficient, whilst also dealing with technology needing to be changed for upgrade, repair, or replacement to avoid obsolescence. And changes in scale, either in physical scale, but more likely in complexity, introducing new equipment, new subsystems, and the required interfaces between these additions. These challenges must be considered when developing long-term robotic solutions, as they affect all aspects of the design, mechanical, electrical, and the control software. This talk focuses on how we in RACE have approached solving these challenges from the control software perspective and the development of CorteX, our framework for producing interoperable, plug-and-play, distributed robotic systems of systems. The problem of creating solutions capable of future modification is nothing new to software development. Software is, more often than not, continuously updated, upgraded, and extended over time. The principles by which we write the code in order to facilitate this development can also be applied to system architecture and the communication of that architecture for distributed systems. CorteX builds on 4 key principles from the object-oriented design paradigm. The first is reusability. For example, a control system developed for a 6-degree of freedom manipulator should work with any 6-degree of freedom manipulator, not just for a specific manufacturer or platform. This is also true for the subcomponents of the control system. So the majority, if not the entirety, of the control system developed for a 6-degree of freedom manipulator should be capable of being reused and extended to form the control system for a 7-degree of freedom manipulator. This reusability and extensibility is vital for efficient development and significantly reduces duplication of work. Of course, in order to facilitate the first 2 principles, modularity is realistically a requirement. Breaking down the control system into components provides building blocks that can be reused in various configurations for different applications, and more can be added in order to extend functionality and capability. However, in order to maximize the reusability of these modules, we need to ensure they can work together in various configurations. This is why the interface between these components is so important. A common approach to this problem is to standardize on a collection of interfaces and ensure all components of the system use an interface from that collection. However, for long-term applications, this can be rather limiting, as new technology is likely to bring new information that may not fit this previously selected collection of interfaces. A future-proof solution should support extensibility, whilst also maintaining backwards compatibility so as to support reusability. This principle is similar to polymorphism in the object-oriented design paradigm. The 4 principles discussed so far aim to create generic control system solutions that are abstracted from the hardware implementation. So for example, if a solution is built using a manipulator from one manufacturer, the majority of the control system should remain unaffected if this is later changed to a manipulator from a different manufacturer. And as long as the capability of the manipulator is comparable, the operator shouldn't really care which one is used, and neither should the operator interface. The final principle we believe required for long-term robotic solutions is the user interface. The human operator is often forgotten when developing control solutions, but they are a key component of the system. If the system is changed, for any of the reasons previously mentioned, the operator often has to adapt to this. In some cases, this just means learning a new feature, but depending on the change and how well the system is designed to accommodate this change, it can mean significant retraining is required. By standardizing components of the control system, we can similarly standardize components of the HMI. The reusability, extensibility, and modularity discussed with regards to the control system is just as true for the graphical interface. The more we can standardize and reuse graphical components between systems, the more consistent and universal the operator interfaces will feel. This should not only reduce the need for operator training or retraining, but also reduce the cognitive load and mental fatigue often attributed to moving between different HMIs for various parts of the system. So how have we implemented these principles with CorteX? Well, first of all, we use the name CorteX to describe our solution, but it can be thought of as a number of different things. First, CorteX is a standardized way of describing systems. Rather than standardizing the descriptions themselves, which is the more common approach to standardization, for example, ROS's various type messages, instead we've standardized the method for describing those systems as a whole. CorteX describes systems as a directed acyclic graph with homogeneous nodes, which we call simplexes. As these simplexes all share the same underlying structure, interoperability, at least at the lowest level, is guaranteed, and discoverability and inspection, or introspection, require no prior knowledge of any part of the system. Simplexes all contain the same fundamental elements. Data, a collection of name-value pairs. Common uses for this data are to describe the current state of the system, often referred to as observations, or to describe the state of the system as we wish it to be, also known as demands, but are also used to store intermediary process values. Relationships. These effectively form the edges of our acyclic graph. As previously mentioned, these edges are directed, either configured as inputs to a simplex or as outputs, and store paths to other simplexes as a source or destination of information. Commands. A collection of commands and their required parameters that can be called in order to change the state and/or behavior of the system. This can be as simple as turning something on or off, or as fundamental as changing the control method used to govern certain parts of the system. They also have a unique ID in the form of a path for easy identification and categorization. And finally, a type. This is where the comparison with polymorphism comes in, and how we are able to standardize while supporting extension and remain backwards compatible. CorteX simplex types provide us with the opportunity to be interoperable at a higher level. While the standardized simplex structure allows us to gather syntactic information about elements of the system, a simplex's type offers us semantic information regarding its purpose and function. They lay down rules for the contents of simplexes that wish to state that they are of that type. For example, a simplex claiming to be of type axis must have a data value called position in order to ensure that any other simplex interfacing to it via a relationship can be sure that that positional data exists. CorteX types can, and should, be standardized in much the same way as the standardized descriptions other solutions use. But CorteX types have 2 key differences. The first is that they form a graph or ontology, where types can inherit from others and extend them. This is where we have the link with polymorphism, because in much the same way that within code you can interface to a class by interpreting it as one of its parent types, this is also true for interfacing to a simplex. For example, your system may not be aware of a specific simplex type of KUKA KR150, but it will be able to fall back on its parent type, 6 degree of freedom manipulator, for example, and interface to it at that level. Yes, this interface may not provide all the extended features of the full KUKA KR150 type, but the system maintains backwards compatibility and functionality that still enable it to be used as a manipulator. Then, later, if this extended functionality is required, other components can be developed to take full advantage of the full interface, without having to change anything on the robot side of the control system. The second difference is that this type graph is distributed, along with the collection of simplexes at runtime. This means, as is also true with the simplexes themselves, no prior knowledge of the types is required. The protocol used to describe the various types is standardized, rather than the types themselves. The simplex model and the supporting type model together form the standard CorteX system description. So to continue the answer to the question, what is CorteX, the second part of the solution is a software implementation of the standard I've just described. At RACE, we've developed a C++ library that allows you to build a simplex model and its supporting type model using a simple and intuitive API that can be incorporated into any C++ application. In order to enable distributed systems, we've developed scalable communication interfaces that allow these models to be transmitted between agents connected via a network, for example. I previously talked about the idea of observations and demands within a CorteX system, but it's the introduction of processing or control that produces one from the other. Within a CorteX system, this control can either come from an external source, such as ROS or MATLAB, but we also provide the option to extend the core CorteX library to add control functionality. This effectively gives developers the ability to add function to each simplex, which is executed as part of a loop cycle using the execution order derived from the directional acyclic graph. This quickly gives the simplex model structure in the form of input, process, output, where simplexes are implicitly considered descriptive or functional based on their role within the system. This paradigm closely follows that of function block programming, so developers familiar with the EN 61131-3 standard would find this very familiar. The addition of function to a simplex quickly turns CorteX from a communication system into a control system, capable of full systems integration and even low-level hardware management. We previously mentioned how important the human operator interface is to control system solutions, and one key use of the ability to distribute a control system is to provide a remote interface. For this purpose, we have also developed a graphic user interface library that can be added to any CorteX application. This GUI works in much the same way as our control system with regards to modularity. Upon receiving a CorteX system description, the GUI will dynamically populate using the type information to select controls and displays best suited for communicating the state of the system to an operator. We've also developed toolkits, libraries containing pre-made simplexes that can be put together in different configurations to fit various applications. These are loaded at runtime and again support the modularity approach to the development and construction of a CorteX control system solution. These toolkits can contain simplexes for implementing various control algorithms, for reading from sensors, and for interfacing to robot hardware. They make it easy to assemble a solution from previously developed components, whilst also facilitating the creation of your own simplexes that may be bespoke to your particular application. Toolkits are often produced together with a GUI library to provide HMI elements to best present the new simplex information to an operator. So now I've described what CorteX is, it's time to focus on what it can do. CorteX has already been used with great success in research and innovation programs, as well as industrial and nuclear-based applications. One of the more recent examples of this is on the TARM, a large piece of legacy jet equipment. The TARM, or Telescopic Articulated Remote Manipulator, is possibly one of the largest robots in the UK and has been moved to our work hall here at RACE. Since its arrival, it's been stripped of its 40-year-old wiring and had a full replacement electrical and control system solution implemented. The TARM is now controlled from an entirely CorteX-based control system, using an EtherCAT bus for communication with a large collection of onboard hardware, including motor drives, load cells, IMUs, and resolvers. CorteX has full control over the 10-meter-long TARM boom. CorteX has also been used to provide integration with a viewing system of HD pan-tilt-zoom cameras and an array of monitors within our control room. This control room also provides TARM operators with a CorteX HMI capable of positioning each joint of the TARM with millimeter precision, provides low-level diagnostic information and a visualization of the TARM's current and target position. This application of CorteX serves as great evidence for its capability with large-scale nuclear remote handling equipment. In addition to this application, CorteX is being used to provide TARM sensor information and low-level motor control as a test platform for a Eurofusion-funded research program looking at the challenges of using long, slender manipulators for the maintenance of the upcoming demo fusion reactor. This research and other applications like it are a great opportunity to expand the use and development of the CorteX software and its supporting toolkits. We'd like to invite academics conducting research in relevant fields that would benefit from having a real nuclear use case to contact us at RACE. We provide free CorteX R&D licenses and are always looking for new applications, new collaborations, and new technologies to expand CorteX capability. Thank you for listening. If you have any queries or wish to discuss collaboration opportunities, please contact us. Thank you.